When we learn a new topic, it's sometimes helpful to have a little preview of what's to come, to have a little teaser or a snapshot of what's ahead. So in this course, we're going to do a lot of learning that's sequential. Learn principle A, build on that to B, and build on that to C, and so on. But in this example, we're going to have a kind of jump ahead, and I'll identify a principle that comes out in special relativity that is very much in conflict with your day-to-day experience, and we're going to see what are one of the consequences of that change. So we'll start by introducing the players. We're going to have Alice and Bob, and throughout the course we're going to use Alice and Bob because Alice starts with A, Bob starts with B, so that's convenient, A and B, and having a male and female pronoun is kind of helpful when we, just to clarify who we're talking about, we can use he and she to distinguish between them as well. Also, you'll see that we're typically going to have one person moving relative to the other, so that we can study a physical situation from two different frames of reference, a frame in which an object's moving and a frame in which that object's at rest. So the scenario here is we're going to have Alice throwing a ball, and Alice is going to be doing so from a train, and the train can be moving or not relative to the ground, and we'll have Bob standing still relative to the ground. Let's say for simplicity that Alice can throw the ball at 3 miles per hour relative to herself. Since Alice is on the train, anyone at rest on the train will say that ball is moving at 3 miles per hour. And if the train is not moving relative to the ground, then Bob would also say that the ball is moving 3 miles an hour, because then Bob and Alice would both be at rest relative to each other, and they would see the ball moving at the same speed, and they would agree on that speed. But if the train were moving, let's say moving towards the right, Bob would see the ball being thrown to the right, and he would see the train being moving to the right, and he would say the speed of the ball would be more than 3 miles per hour because the speed of the ball would be enhanced by the motion of the train. And so from one way to sum this all up is basically that Bob will say that the speed of the ball depends on the speed of the source. In other words, the ball is not always moving at 3 miles per hour. The ball's velocity or speed depends on how fast Alice is moving when she throws the ball. So we call this the source speed matters principle. In other words, according to Bob, the speed of the ball depends on Alice's speed relative to Bob when she throws the ball. If this all seems really basic, obvious, and self-evident, then it should. Everything in our daily lives kind of behaves according to this principle. This source speed matter principle is, according to our daily lives, how the world works, right? But the reason that I bring up this example is because at the speed of light, this principle actually breaks down. In fact, this is one of Einstein's kind of most famous discoveries and points of creativity, really. As a teenager, he had become obsessed with a related question, which is, if instead of a ball, imagine Alice emitting light like a flashlight, and instead of the train moving, 10 or 20 miles per hour, imagine that the train was moving near the speed of light. The question then in Einstein's mind what would Bob see in that case? And Einstein eventually came to a radical realization that the speed of light actually would not depend on the speed of Alice, or the speed of the flashlight in this case. Instead, Bob would measure the photon traveling at the same speed, whether the train were at rest or whether it were moving near the speed of light. So here we have a new principle then. Instead of source speed matters, Einstein is telling us that for light, source speed doesn't matter. It's as if Bob would measure the ball traveling 3 miles per hour, whether the train were moving or not. Okay. If this sounds weird to you, you're not alone. This is a very, very bizarre aspect of nature, but every experiment that has been done to test this is consistent with this idea that the speed of light is always the same, independent of how fast the source is moving. Okay. So now what we're going to do next is explore the implication of the source speed doesn't matter principle. So let's now actually explore the implication of this source speed doesn't matter principle that applies for photons and anything actually traveling at the speed of light. What we're going to find out is that we have a consequence of the source speed doesn't matter principle, and that is that events that are simultaneous for Alice may not be simultaneous for Bob. And we're going to give this the name the relativity of simultaneity. So whether or not events are simultaneous is a relative concept. It's one that depends on reference frame. And another way to think about this is that there's no such thing as absolute time. So for example, if Alice says that 2 firecrackers go off at noon, those 2 events are simultaneous for her, 2 things happening at the same instant of time, noon. Bob would say, actually, no, one of the firecrackers went off before the other. One went off at noon and one went off at 11:59 in the morning. And so what that means is we cannot assign a unique time to a specific event. The time that you would assign to that event depends on your frame of reference. So we'll see this using what's called a Gedanken experiment, which is German for thought experiment, and it was a tool that Einstein used very frequently when developing relativity. These are hard experiments to actually carry out in person, although things like this have been done. But you can reason through the consequences of a thought experiment and see what you find. So our setup again will be Alice on a train. And this time, instead of Alice holding a flashlight, she has a laser beam that can shoot 1 photon to the left and 1 photon to the right. So we'll show that here. Again, this is going to be in Alice's frame. We have Alice on her train, and in the middle of her train we see this blue light bulb looking thing, which is our laser, and it shoots 1 photon to the left and 1 photon to the right. And we've located the laser exactly in the midpoint of the train. So it's a distance L from, the left photon has to travel a distance L to get to the left wall, and the right photon has to travel a distance L to get to the right wall. And since we know that the photons are traveling at the same speed, the speed of light, and they have to travel the same distance, we can infer that they're going to arrive at the same time. So we can bring in a picture down below showing the 2 photons sometime later, and what we see is that they both travel the distance L at the same time, and we see that they arrive simultaneously at the wall. So we can say that left photon hits the wall at the same time as the right photon. And I'll use this moment to identify a couple things about this scenario. Number 1, we've used the idea that distance equals speed times time. And if the distances that the photons need to travel are the same and their speeds are the same, then it will take the same amount of time for them to make that trip. The other thing I want to point out with this example is a drawing convention that we're going to use throughout this course. So we've drawn Alice on the train twice. Each of those pictures represents a single instant of time. The first picture represents the instant of time that the photons are released, and the second picture shows another instant of time sometime later, and that is the time that the photons hit the wall. I've labeled that this is Alice's frame, and in Alice's frame, Alice is at rest. So being at rest means that you're at the same horizontal location in both of these drawings. In fact, everything in this drawing is at rest except the 2 photons. The train's not moving, Alice is not moving, and the light bulb or the laser is not moving relative to the ground. All those objects are stationary. So those vertical dashed green lines indicate that from the first snapshot image to the second, nothing has moved except the photons. We will be using drawings like this throughout the relativity portion of this course, and it's a skill that we all have to practice and we have to master. But the beautiful thing about doing relativity this way is once you've drawn these pictures, the equations that you'll need come out of the pictures themselves. And we'll develop special relativity and the consequences of it by drawing diagrams like these. Okay, so in Alice's frame, there's really not that much to say, right? Everything's pretty straightforward. The photons leave at the same time, they arrive at the same time, their arrival at the walls are simultaneous. Okay, but let's see what happens when we analyze the same situation in Bob's frame. So in Bob's frame, by definition, Bob is at rest, and now the train is moving. The 2 photons are still emitted from the middle of the train, and they're still emitted at the same time. One moving to the left and one moving to the right. But this time, the train is moving, and we've labeled that with a purple arrow that says v train comma Bob, meaning the velocity of the train with respect to Bob is to the right. And we can be very explicit that the velocity of Bob relative to the ground is 0, so he's not moving. So let's see what happens some time later after the train has moved to the right a little bit. Well, the first thing we can see is that Bob hasn't moved. He's in the same place because he's not moving in the frame that we're drawing. He's not moving in his own rest frame. But we see that the train has moved, okay? So the light bulb or the laser in the middle of the train is no longer where it used to be. It's shifted over to the right. And also, the walls have shifted over to the right. And all of these have shifted by the same amount, right? The right wall has gone to the right, the left wall has gone to the right, and the laser beam has gone to the right, such that all of these horizontal gaps are the same because the whole train has just shifted entirely to the right. Now, what about the photons? Well, we know that the photons each travel at the same speed as each other, and there's a single amount of time that has elapsed between the first picture and the second. So the distance equals speed times time equation tells us that both photons will have traveled the same distance relative to where they started. Let's assume that at the second picture, the left photon has hit the left wall, and that tells us how much distance the photons have traveled. So the photons have traveled a distance labeled by this purple arrow. Okay, but both photons will have had to have traveled the same distance. Okay, so at the second picture, the photon on the right will be right around there. So we can draw him in. There we go. So the first observation is that the left photon has hit the left wall, but the right photon is still traveling. It has not yet hit the right wall. But recall that in Alice's frames, the two photons hit the wall simultaneously. But here the left photon hits the left wall before the right photon hits the right wall. And there's a very simple explanation as to why that is. The left wall is approaching the photon, and so the photon and the wall are both acting together to close the gap between the two. But the right wall is running away from the right photon, so the motion of the right wall is working to increase the gap between the two. Now, of course, the photon is traveling faster than the wall, so eventually the photon will catch up with the right wall and hit the right wall. But that hasn't happened yet, as drawn in the second picture. We can label each of these pictures to make that clear. The first picture represents the instant that both photons are launched. The second picture represents the instant that the left photon hits the left wall. And we will actually need a third picture to indicate the time that the right photon will reach the right wall. All of these pictures aside, the main idea is that two events that were simultaneous in Alice's frame, namely the photons arriving, are no longer simultaneous when observed in Bob's frame. So our main conclusion from this thought experiment is that there's no such thing as absolute time. Time is suspect. It's relative. It depends on your frame of reference. We have two events that are simultaneous for Alice. They are not simultaneous for Bob. This idea of relativity of simultaneity is one of the three main pillars, three consequences of special relativity. And we're going to derive this in a more quantitative way to figure out how far out of sync are these two events for Bob, given that they're simultaneous for Alice, and we'll do that more quantitatively. But for now, just recognize that looking ahead in the course are basically three main consequences of relativity. One of them is the relativity of simultaneity. The other is that the rate that a clock ticks depends on its speed. And the third is that the length of an object depends on its speed. And all of those things have no counterpart in classical physics, in the physics of our everyday life, right? There's an absolute time when you tell your friend you want to meet them at noon for coffee. You don't have to say as measured by somebody moving at half of the speed of light or as measured by somebody on the train. We all have the same watch. And objects don't shrink or expand in proportion to their speed. They're all the same length independent of how fast they're going. And the rate that clocks tick is is independent of how fast they're going. That's the classical world. That's the kind of everyday, what we call the Newtonian world. But as you approach the speed of light, those three things break down, and you have a relativity of simultaneity. You have time dilation, meaning that fast clocks that are moving fast tick slowly, and length contraction, namely that objects that are moving fast are shorter. And we'll talk about each of those in turn. So as a parting question then, you might ask, well, why doesn't this happen for objects at low speeds, right? Why doesn't this happen with baseballs and slow-moving trains? So I'm going to pose that question to you, and I want you to think through it. What in our argument here is different for photons than it is for baseballs? And if instead of a photon, two baseballs were shot out in opposite directions on this train from the middle of the train, and Alice measured that both baseballs would hit the walls at the same time because they're traveling half of the distance of the train length, and they were released at the same time, so Alice will say the balls will arrive at the same time. Would Bob also say that the balls arrive at the same time? So I want you to think through that and come up with a reason why they would either arrive at the same time or not, and explain what is the difference between the argument that we just made with photons and a similar situation only using baseballs instead of photons.